What we're seeing here is a flyby of a very important protein that's located inside of your heart that makes your life possible. This protein is a sodium channel that allows for sodium to pass through to the cells in the sinoatrial node, and without this you would likely die. Highlighted are 3 amino acids that are very, very important for this pacemaking property in the heart, and these amino acids are associated with a very, very rare genetic disease called Brugada Syndrome. This new series is going to be dedicated to diving deep into understanding the syndrome, but also biophysics in general. We're going to learn everything from electrophysiology to protein topology and a lot more. And so, with all of this being said, I have a reason for doing this. So let's go ahead and get started. All right, this is going to be the hard part, but at the behest of brevity, I'm going to go ahead and read something to you before we get started on learning about Brugada Syndrome. 28 years ago, a new child came into this world. He was vibrant, and he was able to put a smile on everyone's face. His parents, both God-fearing Mormons, loved their new son so much and wanted him to do great things. By the time he had finished college, he was aiming to go into medical school. He had a passion for helping others. In October of 2023, he got married to a very wonderful woman. He had received a perfect score on his ACT exams, which was quite rare, and had been accepted to one of the most prestigious schools in the entire United States, known for its neurology and cardiology units. It was very clear that he was destined for great things. He was a smart and ready for this new challenge in life. He was on the track to help and save lives while simultaneously getting ready for starting a new family with his new wife and small new wiener dog that they had purchased together. On March 6th of 2025, he was playing basketball with his friends, and when he finished, he went into cardiac arrest. After being rushed to the hospital, he quickly lost brain function. I got a call and I was told that things were not looking very good. Scared and nervous, I jumped on a flight and was down in the hospital within 7 hours. I arrived at midnight. Overnight, his blood pressure started becoming unstable, and then his lungs started to fail. By 5 a.m., I was in my clothes and racing out the door. It just took 10 minutes to reach the room that was trying to keep my cousin alive. His wife, sleep deprived and scared of the uncertainty, was weeping next to him, praying that some stroke by the hand of God would save her husband and alleviate her anguish. The heart monitor still showed signs of a heartbeat, but it was getting irregular and decreasing. By 1 p.m., he was confirmed dead. The cause of this came from a hereditary mutation in the sodium channels in the ventricles of his heart. This is the exact same thing that we were looking at with the protein earlier. These protein ion channels are responsible for the pumping of the heart. When the cells are hyperpolarized, the channels become activated, allowing for sodium to enter the cell. Upon sodium entry, the cells quickly depolarize, which causes them to squeeze, providing the contractility that the heart needs to pump blood. Essentially, these proteins are the pacemaker proteins of the heart. The mutation that he had most likely affected the ability of the channels to become activated. Named after the Spanish cardiologists and brothers Pedro Brugada and Josep Brugada in 1972, this genetic disorder was identified as being a rare and usually livable. While most people with this disorder are usually fine, if they become too active, the heightened cardiovascular activity can be too much for the sodium channels to handle, and they start working arrhythmically, contributing to some sort of cardiac arrhythmia, with atrial AFib being a likely symptom. Based on the last ECG readings, the doctors confirmed that this was likely the cause of my cousin's death. There was nothing that we could have done to save him. This was beyond our control. All we could have done was pray, and we will continue to include him in our prayers. And so I've decided to start this new playlist and many more to follow on introducing the life sciences. I myself have a degree, just finished actually my graduate degree in biophysics, and I want to now project all this knowledge onto you guys so that you guys can become great doctors and great PhDs or whatever you're aiming to do, so that you can become aware of these diseases and cure them. We need people out there to help cure cancer, to help cure syndromes like Brugada Syndrome and so forth. And so with all of this being said, we're going to start this series on Brugada Syndrome. Join me. All of these are going to be free to the public. So let's get started. Okay, so let's go ahead now and get into Brugada's syndrome. At the forefront of this, I just also want to mention, and I'll keep on reiterating this, that I am not a clinician. I'm not a medical doctor. I'm not here to give advice on what to do if you have this issue with your heart, but I'm here to just give information about this syndrome, okay? And we're going to go deep into this. We're going to cover a lot. We're going to cover a lot of biophysics. We're going to cover a lot of electrophysiology. We're going to cover basic anatomy, even some physics, chemistry, biochemistry. We're going to cover everything because the model that I'm using to teach you guys this kind of stuff is a new sort of reinvented model that I've come up with. The idea being that we don't learn from the bottom up. We don't learn basic principles and then build from those principles. We actually start off with advanced stuff to capture your interest. And then from there, we learn general stuff along the way. Okay, so Brugada syndrome is a cardiac abnormality of the heart, okay? Even though this condition is regarded as rare, it has detrimental effects on people who have it. In this video, we're going to cover what it is, how we can understand it, and what we can do to properly address it, okay? Again, I'm not a clinician. I'm not going to give any advice on this. Okay. The heart we can think of the heart as a beating pump. Okay. And one could ask the question, how does the heart beat? Well, we know, maybe we don't know if you're new to biophysics, but if the heart has a clump of cells in it, right? So if we're looking at the heart here, This pink stuff here, this pink zone right here is called the sinoatrial node. Okay, so this is the SA node. This here is the AV node. AV node. We have our two atria, right? Our right atrium. And then our left atrium. Then we have our right ventricle. I'll just say vent for short. And then our left ventricle also. This is the basic anatomy of the heart. And we have so we'll go deeper into the anatomy. We're not going to cover everything, every anatomical feature of the heart right now, but this is really just a brief overview of the four chambers of the heart and where the SA node is. We are focusing on the SA node because this is where the root of Brugada syndrome comes from. Brugada syndrome is a mutation of the sodium channels inside of the cells, or along the membrane of the cells that make up the sinoatrial node. And when we zoom in on the SA node, we essentially have a clump of cells, and those cells along their membrane are going to contain sodium channels, okay? And those sodium channels are going to allow for the influx of sodium into the cells, and that influx of sodium into the cells is going to allow the cells to do something. And that something that we're going to see later is provide contractility, okay? They're going to allow for calcium floodgates to open, or calcium protein channels to open, allowing calcium in. And we know when the calcium enters the cells, that calcium will bind onto myosin, actin, and all that stuff, and provide the contractility effects that the heart needs in order to pump blood, okay? So we have this SA node. We can make sense of where it's located in the heart. So let's go and zoom in on one cell in the SA node and see the diversity of the proteins that exist inside of these SA node cells, right? So the cells that make up the sinoatrial node are unique, and we're going to see why they're unique in a bit, in that they contain sodium channels that are activated upon hyperactivation of the cell. So we're going to get deep into this as well. We're going to talk about what hyperactivation is, but these channels, just briefly speaking here, these channels, they exist in concert with a series of other proteins that outline the perimeter of the cells. So it's not just the sodium channels that exist on the perimeter of these cells. It's hundreds and hundreds of different types of proteins that exist on this is true for any cell, right? They exist on the membrane of the cells. There's going to be hundreds of proteins that exist inside of the cell as well. The proteins that exist on the membrane are transmembrane proteins, okay? So that's going to be stuff like our sodium channels or calcium channels or potassium channels, or even the channels that allow for sodium and potassium to flow through by use of energy of some sort. Okay, same thing here, calcium and sodium channels as well. And then inside the cell, we're going to have these things that harbor a lot of calcium. I'll erase this really quick. Well, we're not going to go too deep into this right now, but the idea here is that we have these organelles inside the cell as well, inside the cell, and these things are also going to have proteins on their membranes, right? So we have transmembrane proteins outside here, like so on the membrane of the cell itself, but organelles inside are also going to have proteins as well. And this the circa pump, it pumps calcium into the sarcoplasmic reticulum, right? So this is the sarcoplasmic reticulum. I'll just write that down. Sarcoplasmic reticulum. Okay, the whole point of the sarcoplasmic reticulum in the cells is to really just harbor all the calcium. What's super interesting about calcium, and what I should put here, I need to correct myself, is that these are divalent, right? Calcium's divalent, so it's got a 2+ on it. Is that the thickness of my pen is okay? So we need a 2+ on all these calciums, just to be correct here. So 2+. So calcium has 2 positive charges on it, as opposed to sodium. Sodium only has 1, potassium only has 1. Those are monovalent ions, cations, right? So cations have positive charge, anions have negative charge. An anion would be something like chlorine, okay? But the cations are sodium, calcium, potassium, zinc, for example. Calcium is unique in that it is divalent. It has 2 charges, 2 positive charges on it, and that the cells, the gradient, the amount of calcium outside of the cell is way, way, way higher than the amount of sodium or calcium inside the cell. The gradient between calcium outside and inside of the cell, in other words, is much more substantial compared to the other ions, compared to sodium, compared to potassium, okay? Calcium is unique in that way, okay, that the gradient is really, really freaking high, okay? And it makes things interesting, right? When you actually think about how calcium is involved in so many cellular processes, it sort of begins to make sense. We'll go into the importance of calcium later. It plays an important role in neurodegeneration as well. It plays an important role in many different types of things. I'll mention also that we have These are also potassium channels. Potassium channels will pump potassium outside of the cell. And these potassium channels, some are going to require acetylcholine. For example, acetylcholine is a neurotransmitter, some won't. Okay, we'll get into these I's. So I, if you're into physics, I is going to stand for the current. So the amount of potassium flowing through this channel. We can quantify the amount of potassium flowing through this channel at any given time span as I, which is the current. Why it's not C is just the current has always been denoted I, the variable I for anything in physics, okay? And you can see I have I funny. So funny, we're really specifically going to look at these proteins when it comes to Brugada syndrome. The reason this is called funny is because these proteins have a very unique property in that they are activated. These sodium channels, they're activated by hyperpolarization of the cell. If you don't know what that means, we're going to get into that in a few minutes. But the idea here again is that what we want to focus on when we look at Brugada syndrome is these channels, okay? We have a long-lasting current, we have transient current calcium, and then we have a countercurrent, right? This countercurrent is when sodium goes into the cell, there's going to be a pumping of calcium outside of the cell. You can notice also that these guys, these are going to let calcium in, and then that calcium is going to enter the circa, and it's going to get stored in here. And then the ryanodine receptors on the sarcoplasmic reticulum are going to allow calcium to get pumped out. So you can sort of track where calcium goes. It's going to end up in the sarcoplasmic reticulum, and then when the ryanodine receptor gets activated, it allows for calcium to get out, and calcium will also get pumped out here, and so forth, right? So so calcium is going to be important. What we're going to look at, though, is this guy right here, okay? So let's continue. So the cells that make up the SA node of the heart have many proteins along their membranes and many proteins inside of them as well, right? So the cells are the most diverse things you could possibly think of, right? They have tons and billions of proteins outside on the membrane, and there's tons and billions of proteins inside of the cell, and there's tons and billions of proteins inside the nucleus and inside the sarcoplasmic reticulum. They're just they're every freaking where, right? They're just everywhere, okay? So these proteins have many properties to them. Of the proteins that outline the membrane of the cells, there's one type in particular that is going to be responsible for Brugada syndrome, which is the sodium channel voltage dependent or voltage gated proteins. Okay, so we have Na, that's sodium on the periodic table. V means that it's voltage dependent. We'll talk about what that means as well. And the 1.5 is just an identifier number, okay? Because you have 1.3, 1.4. We have different slight variations on this sodium channel, okay? And when we were looking at towards the beginning of this video, when we were looking at that three-dimensional model of the protein, that's what we were looking at. I try to color code this stuff, right? So this is green. The protein that we were looking at in the beginning of this video is green as well. So I try to match colors, and I try to point out when I'm not matching colors as well. Anyways, these sodium channel voltage gated proteins are the primary reason why these cells have a pacemaking property to them. And let's see why this is the case. So this is a diagram. This diagram is going to show us what so this is the potential of the cell. What's the potential? The potential of the cell is the difference. When we look at, here's our cell, for example. We have charge outside. We have some charge outside. We're going to have some charge inside. When the charge outside, so let's suppose we have positive charge out here and negative charge in here. Okay. So when say we have positive, let's do it like this. Actually, let's say we have resting so a negative 70 potential means that the difference in charge out here, compared to the charge in here, when we take that difference, the value is going to be negative 70. Okay. So that's how we calculate the potential. The potential, again, is the difference in charge between the outside and the inside. Okay. The difference in charge between the outside and the inside of the cell. Okay. So what does this diagram tell us specifically? Well, what this is showing us is that as the potential increases, okay, so as we talk about this in terms of polarization or depolarization, or depolarization and repolarization. The difference here is huge. It's negative 70, right? So that means that the cell in here, the inside of the cell, is negative, much more negative compared to the outside of the cell. We can almost think of this as if the charge out here was 0, the charge down here in here is going to be negative 70. Okay, as this value goes to negative 50, right, that means that there's going to be, we're losing negative charge inside the cell, or we're gaining positive charge. Okay, that gain of positive charge is going to be the influx of sodium, because sodium has a positive charge on it. So the influx of sodium, right, is going to follow this green curve. Okay, that means that we're getting more positive inside the cell. Okay, and then there's this really fast depolarization. Okay, this really fast depolarization is going to be associated with a fast influx of calcium into the cell. Okay, that fast influx of calcium into the cell is going to be followed by a repolarization. Okay, all the way down to here. That repolarization is given to us by these potassium channels. Okay, and then we start at the beginning again. We go back to slow depolarization, and this is what we're calling the pacemaker potential for these green guys here, because this is like an automatic switch. This is acting like an automatic switch. What's happening is that we have initially, so this is time, okay, we have initially our proteins, our sodium channels, the influx of sodium starts coming into the cell, and then once this hits a number around negative 30, then this switch turns on. This switch it's going to turn on full force. It's going to let in so much calcium, okay? But then once it lets in so much calcium, then these guys are going to turn on, and it's going to push out charge, okay? So it's like switch sort of thing. It's like, so, and these things are always going to increase in value. And so because of this increase in value, these things turning on when the cell is hyperpolarized, again, hyperpolarized means we have a polarization value of around negative 70. Right, we get that switch, that turning on of these proteins right here. What it means by turning on means that they're opening and they're allowing for the sodium channels to come in, right? But we can sort of think of this as switch, right? This idea that you have this, these things are slowly going to bring in the sodium, and then boom, boom, and then slowly bring in sodium again, and then boom, boom. Okay, so it's because of these guys that we're always going to be having that sort of automatic switch being turned on with respect to the calcium coming into the cell. Okay, and again, recall that all of this occurs in a cell in the sinoatrial node. Okay, so that switch is occurring in these cells which provide the calcium needed. The calcium comes in at very fast frequencies because of these cells. It's boom, boom, calcium, boom, boom, calcium. And that's what the heartbeat is, okay? Okay. So what I like to do when I study biophysics, anything biology related, is I like to compare these diagrams with other diagrams. And I think this really helps a lot in understanding anything when it comes to biology and biophysics, and even in physics and even in chemistry, is when I make comparisons, I start getting more aha moments, okay? So let's compare the potential diagram of our SA nodes, our SA node cells, because they're very unique cells. Let's compare them to your standard neuronal cell, okay? And let's see what these things look like. So we have this resting membrane potential. The resting membrane potential is okay, I have this green because this is also an influx of sodium. This is an influx of sodium, right? But the idea here is that when we look at the depolarization, they're both very fast, right? But we have the shape is a little bit different, right? The shape is a little bit different. And then we have this repolarization, and then resting membrane potential, and then slow depolarization. We see here that here we have resting membrane potential, right? Here it's always depolarizing. That's the key, right? Is that these things are really essentially always on, okay? These things, they become activated when the cell is sort of in that resting state. Here, these proteins are different than these proteins in that they don't have that property. They're actually resting. They have a resting potential. So there's going to be, so these things are always bringing in more and more sodium, whereas these things, they'll bring a little bit of sodium in, but once that sodium reaches a value, then the depolarization happens. Here, sodium, and then depolarization happens. So there's no threshold, in other words, here. There's no threshold by which these calcium channels are going to begin to open, okay? So we can stare at these two diagrams. You can pause the video if you want to take a look at the comparisons between these two diagrams. Again, this is for the SA node cells, SA node, and this is for neuronal cells. Okay. So let's continue. All right, so before we continue, I just want to reiterate this again, because I'm not on any time crunch here. These are two fundamentally different cells, okay, when it comes down to understanding the difference between these polarization diagrams, okay? One is essentially always on because this is always increasing, okay? The other one is not always on because of this flat line. We can sort of think of it in that way, okay? Okay, so let's continue. All right, so the reason for this this is lack, not LASK. The reason for this lack in a resting membrane potential is because of the type of sodium channels that allow for the flow of ions through the membrane. Okay, so these are a very specific type. These are a very specific type of sodium channel, and because they're a very specific type, they have this quality of this positive slope here. They're always on. When the cell is hyperpolarized, theoretically, in neuronal cells, again, that hyperpolarization doesn't turn the sodium cells or the sodium channels in those cells on, whereas in the SA node, hyperpolarization is actually contributing to turning those on. So that's the difference. The channels will slowly increase the flux of ions through the membrane of the channel, whereas in neuronal cells, the action potential is at a steady state. Okay. This is to say that the SA nodes are always working, right? So you have neuronal cells there's some leak into the neuronal cells of sodium, but there's going to be some outflow of positive charge also from potassium. So this sodium potassium leakage, it's always sort of happening, but it's very baseline. It's very, very negligible. Whereas in the SA node, that sodium is creeping in, and then that's what's going to cause that snap in the calcium levels, and then a drop in the outflux of potassium, and then increase again, and you see how this works. Okay, so again, slow depolarization, that is sodium entering the cell. Fast depolarization, so I'll just say sodium enters. Fast depolarization is calcium enters. Repolarization, that's going to be potassium out, and then back to slow depolarization. Whereas in our neuronal cells, that it's different, right? In our neuronal cells, we have sodium entering, and then fast sodium entering. I didn't actually go into that. That's kind of a topic for neuroscience, but this depolarization is not calcium entering the cells. This is actually sodium, but that it's a different type of channel that's allowing for that fast sodium entry into the neuronal cells. There's another type of cell that's going to be relevant to us. That's the cardiac cell. That's the cardiac muscle itself, right? So you have the sodium, so you have the SA node, right? The SA node is what's contributing to that spike. Those are the cells that are contributing to that spike in calcium. But then you also have the cardiac cells, right? So cardiac muscle, it has an action potential. And so we can look at this also. So the action potential diagram for cardiac muscle is quite different than both the SA node and then neuronal cells. In cardiac muscle, what we have initially is potassium is flowing out. Okay, the potassium, we have this steady state of potassium flowing out of the cardiac cells. Okay, so we have potassium out, and then we have sodium in, and then potassium out again. This is a different type of channel, which is why I have it in yellow. But this is potassium out again, and that potassium out, we have. I say potassium because I have color-coded potassium for blue. Red channels are going to be calcium. Green are going to be sodium. I'm going to try to keep that constant throughout the whole channel, by the way. But the whole point here is that these are actually quite different, and they're different in that the shape is very different, right? They're not always on. They're only on when this fast sodium channel happens, right? So, and then we have this purple bit. The purple bit is calcium coming in, and calcium sort of plateaus. Calcium plateaus here, so this is calcium plateau. And then we have repolarization of potassium out again. And so, and in this diagram, we can see it like this, right? So we have potassium out, then a very fast influx of sodium in, and then some potassium out again, which brings us back down. Again, when positive, so a lot of positive charge is going to enter the cell, that's going to bring us up to a bunch of positive numbers here. And then positive out means we're getting more negative, so we're this small decrease. Then we get a plateau, and then we get this repolarization back down to minus 90 actually. So in the other cells, you notice we have this minus 70, right? We have minus 70 here, whereas in the cardiac potential, we actually at a lower repolarization value. So, and then this plateau on average is about 200 milliseconds. Okay, and this calcium, this is like calcium flooding the channel, sort of slowly, steadily, or not flooding the channel, flooding the cell, and that when that happens, that's where the source of calcium comes from. To then you have your myosin and your actin filaments your myosin, and actin. If you're not familiar with the myosin-actin mechanism, we'll go over that. That plays a big part in Brugada's also. But right now we're just looking at potential diagrams for these cells because we want to sort of get a lot of these graphs out of the way. But anyways, this is so we have the SA node. We have its profile, its potential profile. We have neuronal cells. They have their own potential profile. Then we have we have the cardiac cells, and they have their own potential profile as well. There's another one that's smooth muscle. We're not going to really talk about smooth muscle yet. It's a weird one. But these are the three sort of big things that you should know if you're going into med school. You obviously have to know this kind of stuff. If you're going into biophysics, again, very necessary to understand this kind of stuff. And we'll get deeper into this in a separate playlist when we're just talking about electricity and cells. This is what we want to know so far right now, just for the sake of brevity and sort of keeping on track with Brugada syndrome. Okay, so here we can notice some differences, but also there's going to be some similarities. In terms of similarities, the repolarization curves look very similar. The reason for this is because these channels are similar in both cells. The differences are stark though, okay? And we sort of saw this already. I sort of talked about it. To get calcium into the SA node, it takes fewer steps compared to the cardiac cells. Notice here, calcium, here this is a calcium influx, this is a calcium influx. If we have the steady state, this is just good. The steady state, it's like step 0 or step 1. Right after that, we get this huge spike in calcium. Whereas here, we have steady state, but then we need a spike in sodium, and then a little bit of outflow of potassium, and then we get that calcium. So there's more steps, right? So if this was step 1, this is step 2. This is step 1, this is step 2, step 3, and then step 4. Okay? These are different phases. These correspond to these different phases on this diagram here. But we have more steps. We need to go through more steps to get to calcium influx. Okay? In the SA node, cells, in the SA node cells, the calcium channels open almost automatically, whereas in the calcium cells, in the cardiac cells, they require potassium efflux before they turn on. So where does Brugada syndrome fit into all of this? Well, in order to address this question, we need to understand something about ECGs or electrocardiograms. Right? So electrocardiograms, ECG is electrocardiograms. And this is how people used to diagnose heart problems way back in 1960s, 70s, 80s, when they knew how to put electrodes on the body, and they knew how to take electronic readings of the pumps of the heart and all this. And this was really all they had before they were able to get higher tech equipment, because we were sort of in that golden age of developing techniques and measuring conductance of proteins on cell membranes. We were sort of just getting into that by the 80s, where we were starting to understand how patch clamp would work, whole cell patch clamps would work, and stuff like that. And we'll get into that in future videos. But back then, during in the 70s, 80s, 90s, a lot of people were just looking at electrocardiograms of people who had these heart issues and seeing, oh, that's an interesting looking graph, I'm going to name that, and this is a new disease sort of thing. So this was, as I mentioned before, in 1972, the Brugada brothers, both cardiologists, discovered this irregular pattern in some ECGs that some of their patients had, and they decided to name it Brugada syndrome. Okay, and how does an ECG work? We want to understand exactly what all this is. What we've been able to do so far is look at the action potential for the SA nodes and what the action potential looked like for the SA nodes and even the AV nodes. This is the SA nodes we've been looking at specifically, but everything holds true for the AV nodes as well. They have this characteristic pattern that we've looked at already. We've looked at these two patterns. These two patterns are right here, okay? Whereas for cardiac cells, the rest they kind of look like this. And for different regions on the heart, they have a little bit of a steeper profile. So in the atrial muscle, it looks like this. In the bundle of His, the diagram looks like this. And bundle branches and so forth. And we can see where all these are located here, right? So we have the SA node and the AV node. Then we have our atrial muscle. This is going to be this guy. So when this one squeezes, when this guy squeezes, blood enters here. Okay, this guy's going to squeeze, blood goes to the rest of the body, right? Rest of the body comes, as it goes through the rest of the body, the blood becomes deoxygenated, dumps into this right atrium, and then from the right atrium, the blood goes into the right ventricle. Right ventricle is going to squeeze. There should be blue in here, whatever. The right ventricle is going to squeeze, and that's going to send blood to the lungs, okay? The lungs are going to oxygenate the blood, and that's going to come back into here and come back. They're also going to come back into here, right? So red is oxygenated blood, blue is deoxygenated blood. This region here, that should be blue. And so when these things squeeze, that squeezing, it comes from the calcium, this calcium right here in the cells that outline the muscles of these ventricles, right? And so their action potentials look like this. So they all look like cardiac action potentials. When we add all these up, we can see now, so we have a little tiny orange bit that's going to be initially the SA node starts, and then SA node is going to send signals to our atrium. Our atrium then is going to squeeze. By the time that signal gets to the atrium, a little bit more time, a tiny little bit of more milliseconds pass, and that signal gets sent to the AV node, okay? That signal from the AV node, so here's the AV node curve, that's the blue one. Then the dark blue one is going to, so the signal is then going to get passed to the bundle of His. That's going to take a little bit of time, okay? And the bundle of His then is going to contract, and that's what that muscle contraction is going to look like. And then the bundle branches follow, and then the Purkinje, and Purkinje fibers follow, and then the ventricular muscle follows, okay? And so when you add, so this is time, right? SA node starts, and following the SA node is everything else. And when you add all these curves up, you could see this value here is going to be really high compared to this orange value. So the pink value is a lot taller than the orange value, okay? And we can see that that's actually, so that's going to be, so this massive peak right here, that's going to correspond to this pink right here. Then there's going to be a little tail end of blue, light blue, which is going to be right here. And then dark blue, a tiny little tail end of dark blue, which is going to be like right in here, because that's a high value. And then a little bit of yellow, okay? And then followed by a little bit of red. And then the rest is dominated by the ventricular muscles, right? So the ventricular muscles is going to give us all this here. And the reason we have these flat lines and some of these curves is because these guys are negative, right? So when we add these values here, so like a lot of these values are going to be negative because we have negative numbers. So when we add negatives, these positive values will go down to negative values, okay? So when we add all of these up, we get a curve that looks like this, okay? So let's sort of dive deep into this curve and take a look at we're going to assign points to this curve. And then this is going to be sort of the diagnosis that a lot of people would look at, and they'd be like, okay, this guy has some syndrome because this curve is too high, or this curve and this curve are merged together, or something like that. what can we deduce from that? Well, if we know that what constitutes this curve are all of these components, if we see, say, for example, if we see that this here is too long, like that this curve, say, looks like that pink looks like that, well, what would that mean? That would mean that something's wrong with the atrial muscle, okay? So that's really how a lot of these diagnoses happened. Let's go ahead and take a look at a lot of these intervals. So we're able to add up all the electrical signals from the various parts of the heart, and when we do, we get an overall electrical signal for the heart over the course of one beat, okay? The result is the following wave pattern. So this is what we had before, but now we're putting some words to this. We have a PR interval, a QRS interval, a QT interval, and a T interval. Then we have a PQ segment and an ST segment. We label P curve, or P point, or this here is the P curve. This is the Q point, R point, S point, and then T curve. So P, Q, R, S, T, like in the alphabet, okay? PR interval, this is the interval. Again, we can sort of make sense of this now. This interval is the interval in which the atria depolarize and the electrical signal gets sent to the Purkinje fibers, okay? So all of that happens here. So depolarization, signal sent, okay? The QT interval is going to follow, and this is the depolarization of the ventricular muscles, which is quickly followed by repolarization of the AV muscles. So when there is depolarization or squeezing of the ventricles, the SA node, because that already happened, everything in the SA node already happened and the atria already happened, they're already going to be in the process of repolarizing. So two things are happening here. There's depolarization of the ventricular muscles, and then number two is repolarization of the SA node, AV node, and the atria. And then the T interval, the ventricles here are repolarized. Okay. And then we get back to the beginning. So how do we measure this? So I talked about putting the electrodes on the body and everything. Let's take a look at actually, from a physics perspective, how this is measured, because we want to be able to look at this and we want to be able to see what Brugada's looks like, okay? So one thing that we need to take into account is how the ECG is actually performed in the clinical setting, okay? Again, I'm not a clinician. Again, I'm going to reiterate this throughout the video. I am not here to give you advice on what to do if you have Brugada's. I'm here to teach you about Brugada's, and that's it, okay? If you want advice on this, you need to go to your doctor, and you need to tell him this is what you have. You can take genetic tests, you can do all this stuff, but again, I'm here not to tell you what to do. That's not my place, okay? What I'm here to do is to teach you about this so that you can have this knowledge and then tell your doctor what you think or what you think you need to do, or ask your doctor for advice. So what we're measuring when we measure different leads is the magnitude of an electric vector coming from the heart. If our electrode is located in the opposite direction of where the vector is pointing, then we get an inverted reading. So for Brugada syndrome, we'll get into there's three different patterns for Brugada syndrome. Let's take a look here at what we're looking at. So here's our heart. Our heart is located a little bit shifted to the right under our pec muscle, and that pec muscle, we can draw sort of a circle around our heart, and then different points and degrees around the heart. So we have 0 going clockwise, we have positive; going counterclockwise, we have negative. All right, and what we can do is we can say, well, let's put electrodes. We could put an electrode here, we could put an electrode here, put an electrode here, here, and here, and here. Okay, if the heart's beating in this direction, what I mean beating in that direction is that the atria squeezes in a direction, right? So you could sort of think of it's squeezing the blood in the direction of the ventricles, okay? And that squeezing is followed by the electrical current that's sent by the cells, all right? Because if we go back to the beginning here really quick, that current, these cells are quite literally connected by tiny little gap junctions. So the signal that's produced in here from the sodium channels, okay, and then you get an influx of calcium. The calcium's going to flow through these gap junctions, and this cardiac muscle is going to start pumping. So this one's going to pump millisecond after, this one's going to pump millisecond after, this one's going to pump. So you have this in time, sort of this squeezing towards a direction, followed by electrical signals, because you have that positive charge traveling down down the muscle. Okay, so in general, the net outcome is going to be an electric signal that points in this direction. Okay, so if you have an electrode here, you're going to have inverted readings. Okay, because your values are going to be negative because this arrow is pointed in the opposite direction of your electrode. And typically what you get are 12 electrodes, right? So 6 that are sort of in front, and then 6 that go behind you a little bit. Okay, I'm not going to get too deep into this, but that's generally the physics of how the ECG works. Okay, let's take a look at what some of these look like for Brugada syndrome now. So a normal ECG pattern is going to look like this. All right, where you have your QRS curves, your P and your T curves as well. Type 1 Brugada syndrome, this is the most severe of the two. We have something that looks like this. This is a covered ST segment. So here's our ST segment. This thing, right? This plateau right here is essentially covered all the way up to the R value here. We don't even have. It looks like this, right? This is a covered ST segment. Here for type 2, or the type 2 ECG pattern for Brugada's looks like this. So it's a little bit more diminished. And then we have another saddleback segment that looks kind of the same, but the curve here is more profound than this one. This is type 3. Type 2 and type 3 are not as severe. What does this tell us when we look at these curves? Well, when we look at these, the AV node, right? So we look at our AV node that happens over here. Something is happening in the Brugada syndrome where in the AV node the cells aren't repolarizing properly, right? Because here this is repolarization of the AV and SA nodes, this whole region right here. Something is going wrong in this interval. So we have repolarization of the AV node. So repolarization is a big problem in Brugada syndrome. What does repolarization look like again? Well, repolarization is this process right here. Okay, that process. So we now have sort of a clinical outlook on what Brugada's looks like. What we're going to do next is we're going to dive deep into the protein structure and the topology of the protein that we're looking at to get a better understanding of what Brugada looks like, Brugada syndrome looks like. So with that being said, make sure to hit that like and subscribe button. Again, I'm not here to give clinical advice on anything. I'm just here to give you information, and I will see you guys in the next video. Bye.